Now things become exciting because we've analyzed the change in entropy from a microscopic molecular point of view. Now we want to approach the calculation of entropy from a macroscopic point of view. And to do this, we come back to our friend the Carnot cycle, which was the analysis that taught us how to calculate the efficiency of a heat engine. And remember that our heat engine was driven by the input of heat through the high temperature side, the exhaust of heat through the low temperature side, and the execution of work that resulted from the conversion of heat to work. And as we recognized, it's extremely difficult to convert heat into work, and that's why automobiles have an efficiency of only 15% in converting the energy contained in gasoline to the actual motive force of the automobile. So we're going to come back to our Carnot cycle, and we know that we could write the efficiency of that Carnot cycle as the work produced divided by the heat added. And another more straightforward way of saying that is it's what we get divided by what we invest. That is, the work that we get out versus the investment of the combustion of the fuel that creates the inflow of heat into that Carnot cycle. Well, we wrote this then as minus, and we put the minus sign in front because in chemical thermodynamics, work done by the system on the surroundings is negative. So we write the work then as the sum of the work on leg 1 plus the work on leg 2 plus the work on leg 3 plus the work on leg 4. And then we divide that by the heat that goes into the system, Q in. And indeed, that's the work we get out for the heat we put in by virtue of the combustion of the gasoline. Well, when we worked through that, which was a major part of the previous chapter, chapter 3, we calculated that the Carnot efficiency compressed down to an incredibly simple expression. The temperature of the high temperature side of the cycle minus the temperature of the low temperature side, T cold, divided by the temperature of the high temperature side. But we can also write this as the sum of the heat that enters on the high pressure side plus the heat that exits on the cold side divided by the heat that comes in to the high pressure side. And remember, we could do this very quickly because the Q in is indeed the Q that comes into the high temperature side, but we also recall that leg 2 and leg 4 were adiabatic. So if we're looking for the heat exchange, those terms drop out. In fact, they cancel in the work term explicitly. That leaves us with the first leg and the third leg. Those are isothermal. And in the case of an isothermal expansion or contraction, the work is exactly equal to the heat except opposite in sign. So that simply clears up the negative sign, and we can substitute in the heat coming in leg 1 and the heat in leg 3, and that gives us this extremely simple relationship between the Carnot efficiency, the temperatures, and the heat exchange in that cycle. Well, what does this have to do with entropy? Well, it turns out that this is the foundation upon which the macroscopic formulation of entropy was deduced, because if I take this expression, that gives me 1 minus T cold over T hot, and on the right-hand side, that gives me 1 plus Q cold over Q hot. If I subtract 1 from each side, that gives me minus the ratio of the temperature of the cold side to the hot side is equal to the heat extracted on the cold side divided by the heat added on the high temperature side. All right, let's multiply this through by Q hot and divide it through by T cold. That will give me minus Q hot over T hot is equal to Q cold divided by the cold side temperature. But if I move that over to the right-hand side, that gives me 0 is equal to Q cold over temperature cold plus Q hot over the high temperature. So it turns out that that expression is the foundation upon which the macroscopic determination of the functional form of entropy is built. Well, that means that if I break this trajectory around the Carnot cycle into small increments, I can write the integral of the differential form, that is, the tiny increments of heat added along that high temperature side, divided by the high temperature, plus the integral of the heat released on the cold side divided by the cold side temperature. That is equal to 0. Or I can write this a slightly different way. I can equate this to the integral around the entire cycle, which I can represent by this circle, of the change in the heat added in each step. And I know when I'm coming around a Carnot cycle that I'm doing this reversibly in those very small increments divided by the temperature. That quantity is equal to 0. But if, when I go around that full cycle, the dq on a reversible path divided by the temperature, if that's equal to 0, then that means that that quantity is a state variable. I've come back to the same point, and it's invariant. And we know how important state variables are. In our development of the first law of thermodynamics, we recognized that the internal energy of the system is a state variable. That is, whatever its state is, you can calculate it independent of how it reached that point. That is, independent of what pathway. The same is true of enthalpy. It's a state variable. Same thing is true of temperature. The same thing is true of pressure. And the same thing is true of volume. Those are all conditions of a particular state of a system which are completely independent of how they reach that state. And so we now have the markings of another variable, which is a state variable because when we come back to the same point, it has exactly the same value, which is to say when we went around the cycle in reversible steps, that quantity remains invariant when we come back to the original position. So let's summarize. For our reversible cycle, we deduced, because of the virtue of the Carnot cycle, that QH divided by TH plus QC divided by TC is equal to 0. When we broke that down into tiny increments, we can write that the integral of dq hot over T hot plus the integral of Q cold over T cold is equal to the integral of going around the full cycle of dq reversible divided by the temperature. Now we say, well, what is that state variable? It's clearly of great importance. And the hypothesis is that that quantity, namely the differential incremental addition of heat and the extraction of heat during that cycle on a reversible path divided by temperature, is indeed exactly equal to the change in entropy. And so that is the basis for the macroscopic formulation of entropy. So now on the one hand we have the microscopic formulation from Boltzmann, and now we have the macroscopic formulation because we've found a state variable that has elements that look like entropy, but we don't know yet until we prove that the microscopic calculation of entropy is exactly equal to the macroscopic. then and only then will we know that we have the proper mathematical representation of the macroscopic form of the change in entropy.